All right, so before we kind of get jumping into things, everything up to this point, all the Learn Smarts, Connect, Excels, everything should kind of be graded, and grade should kind of reflect all your scores. Everything should be up to date. We currently have these two assignments that are sitting out there. So the Connect, you should be able to make your way through the vast majority of that Connect assignment. The Excel assignment, we have only went over like the first third of it, so that's not due for what, another kind of what would be next Wednesday. We will kind of cover the topics today, but we probably won't look at the Excel portion until Wednesday's class. But after Wednesday's class, we should have everything needed to kind of get through that Excel assignment as well. If we don't quite get through there, I might push the due date up to like next Friday. Just give you a couple extra days, but I think we should be able to get through everything by the end of Wednesday's class for that Excel assignment. But you can work on like the first third of it right now. We've already went over that. Okay. Any questions from me before we kind of jump into things today? Okay, so where we left off was we were talking about, I think we ended with like picking up biases in existing samples. And I can't remember exactly how much we covered last week or where we exactly left off, but it was around this point where we were thinking about, I can look at my sample mean, and I can take a sample of a bunch of different sizes, right? So maybe I take a sample of size 10 or 50 or 100. And from that sample, I can calculate a mean. We'll call that a sample mean. Right? So maybe I'm interested in the income in the US. I take a random sample of 100 people. I calculate my sample mean income from those 100 people. I write that number down. I randomly sample another 100 people. I calculate the sample mean from those 100, and then I write that number down. I keep on doing this, right? Eventually, I'd end up with maybe something like 1,000 different sample means. But once I have those sample means, if they're like in Excel, I'm storing them in Excel, I very easily could use that average function and stdev.s function to find my standard deviation and my mean of those 1,000 different sample means. I could also take those 1,000 different sample means and look at like a histogram or a frequency distribution. So what's going to end up being true, if I'm sampling from a variable that's normally distributed, my sample means will be normally distributed as well. Think about the easiest example where my samples are only of size 1. So I randomly select one person, I write their income down. I randomly select another person, write their income down. If my samples were all of size 1, the distribution of my sample means will be the exact same as the distribution of the original variable I'm sampling from, right? Because I'm only taking one person's income to calculate my sample mean. So what ends up being true, no matter what sample size I take, once I have those 1,000 different sample means, if I then calculate the mean of those sample means, it ends up being just whatever the original mean of that variable I was sampling from was. So if I take samples of size 100 and calculate the average income for all those different samples of size 100, I then take the mean of all those sample means, it'll be whatever the average income in the US is. Think about it this way. Let's say the average income in the US is 50,000. I take a random sample of 100 people. I calculate the sample mean. I might see 48,000 as the mean. I take another random sample of size 100. I calculate its mean. Maybe I see 52. Right? So I'll see sample means that are kind of all over from that original distribution. But as I take more and more samples, I'm going to have every single part of that distribution equally represented. So for now, if this isn't quite, if you're not quite convinced, by the end of today's class, I'll show you using a data set how we can prove to ourselves that the mean of my sample means will always be whatever that original mean of the variable I was sampling from was. Okay? What also ends up being true, and once again, I'll prove this to you later today, is that if I'm looking at the variance of those sample means, right? If I had them all in Excel file, I could find the variance of those 1,000 sample means. It'll be the variance of the original data we sampled from, but dividing by that sample size. We want to think about this. If I took samples of size 1, well, I'm going to end up with sample means that just look like the original data I sampled from, right? Because I'm only taking one person to calculate my sample. So originally, when that sample size is 1, the variance of my sample means is the same as the variance of the original data or the original variable I'm sampling from. So if I think about income, I could take a random person, just like the person at random. Maybe I see their income is 500,000. Right? They just happen to be one of these people far on the right side of the distribution. But if I take samples of size 100, it'd be very unlikely for me to see across 100 people that the average income is 500,000, right? I mean, that's almost impossible if I'm truly selecting people at random. So as I take higher sample sizes, like going from like 1 to 100, notice what's going to happen to that variance of my sample means. My sample size is going up, it should decrease that variance I see on my sample means. That kind of makes sense. I'm just looking at one person. Any one person could be only making $10,000 or $500,000. But if I'm averaging it out across 100 people, it's very unlikely I see a sample mean of $10,000 across 100 people or $500,000 across 100 people. So that variance on my sample means is directly related to whatever the variance or the variation that exists in the original variable, but it's decreasing as I take higher and higher sample sizes. So these two things, for now, you'll have to believe me, but I'll end up proving to you using some data in just a little bit. Okay? So our sample mean can have its own distribution. If we sample from a normally distributed variable, those sample means will also be normally distributed. Right? So we'll kind of go ahead and kind of look a little bit ahead here in the board. But the mean of those sample means is always the population mean of whatever variable we sampled from once. And the variance of those sample means is just the variance of the variable we sampled from divided by our sample size. So hopefully we kind of remember what those two things represented. Lowercase n is our sample size. Sigma squared represented like the variance in that original variable we sampled from. So we think about this sample variance. Okay? Or sorry, actually the sample variance. The variance of my sample means we've got two things that are influencing it. The original variation of the data, which that makes sense, right? If the variable I'm sampling from has a wider variation to it, so will the distribution of my sample means. But that n, that sample size, I kind of worked through the intuition behind why it would decrease that sample variance. But let's think about what that does for it. So, if we think about going from smaller to a larger sample size, let's say I've got, a bad marker. Let's see if this blue one works. So let's say I'm thinking about the distribution of my samples. So maybe originally I start out and that variance of my sample means is something like, I don't know, 10. And maybe that's when I had samples of size 50. I then increase the size of my samples to 100. What's that going to do to the variance of my sample? So if n goes up, what's going to happen to the variance of my sample? If I divide by a larger number, what's going to happen? It's going to get smaller, right? So having a higher sample size, I know that my new variance is going to be higher. Just using some examples, like toy numbers here, but just so you think about it. So, why did I write this higher? It's not going to be 20. We said a higher sample size decreases it. So maybe now it's something like 5, right? Relative to before was 10. So we have this lower variance or smaller variance. What's that going to do to my distribution? we said that a different mean would shift my distribution, it was norm distributed, but a lower variance is going to do what? Maybe it's easier to think the other way. What would a higher variance do? It means there's more variation in the data, so we said that would flatten my distribution, right? Or kind of decrease the height. So if I have a lower variance, that means it increases the height or makes the distribution more peaked, right? So it's going to look something like this. And the reason we know that's going to occur is if we have lower variation to the data, then values further from the mean, remember, to think about the mean of these distributions are the same. Values further from the mean will be less likely for us to see when the variance is lower. And values close to the mean are going to be more likely for us to see. Okay? So in practice, we only usually get to take, or we only have one sample to work with. Okay? So if that's the only sample mean I can observe, and I'm using it to make inferences about the population, I want to make sure that sample mean is going to be close to whatever that true population mean is. So if I'm looking at only taking one sample, I'd rather have a lower variance to my sample means, because then I can guarantee if I'm only choosing one sample mean, it's more likely to be one of these values that are near that population, even if I can't see what that is, right? Even if all I can see is my sample, I know that it's more likely that sample mean will be close to the population mean because the variance on my distribution is much lower. So that's why we like higher sample size, right? It's going to guarantee that I'm seeing a value that's closer to that population mean, or making it more likely. I shouldn't say guarantee, making it, increasing the probability. Okay. Any questions on this? Okay, so we've got this distribution of sample means. I said it was normally distributed. Another way that we might start to write out our standard deviation, it's the same as before. It's still the square root of the variance, right? So it's still the square root of that variance. But if I rearrange things a little bit here, taking the square root of something squared, that's just whatever that, what that number is. And then distributing that square root to the denominator, we'll have that square root of n in our denominator. So just two different ways of writing the same thing. I'll start kind of using both ways because in certain topics, we're going to be more likely, or it's going to be a little bit easier to use the standard deviation. In other situations, it might be more, might be easier to use just that variance set. Okay? So we'll start looking at it both ways, but they really are just the same, or two different ways of writing the same thing. Okay? And don't worry too much about this. There are some situations where we want to make sure that the sample doesn't get too big relative to the population, but that's not going to be anything we really run into. Our population sizes are so large, it's going to be almost impossible for us to have a sample that even remotely gets close to the size of that population. So if we think about some actual numbers to this, if I've got some variable and let's say it's a birth weight. So I have a bunch of births that occurred in Indiana. I think actually I'll use this data set later on. I have every birth in 2004. I calculate the population mean and I see it's 3,287 and the population variance is 360,000. This is like this isn't a very realistic example in the sense that I have the actual population data here, but it's nice because it allows me to see that okay, I can observe the population data, but I can also observe just a sample from it. And I can make sure that these things that I'm telling you hold. So I'm looking at the distribution of sample means. And the original variable I was sampling from had that population mean of 3,287. It also had a variance of 360,000. What should be true is that the mean of my sample means will be equal to whatever that mean was of the original variable I'm sampling from. So if I'm looking at these sample means of size 36, they should have a population mean, they should have a mean that's the exact same as whatever that population mean was. Now the variance on my sample means should be the original variance of the data I sampled from divided by my sample size. Well, I took samples of size 36 here, right? So I end up with what? 10,000. Here I said, well, what's the standard deviation? Well, to get the standard deviation, once I've calculated the variance, just the square root of that. So it's equal to 100. So as long as we have that information about the original variable we sampled from, right? We have the original variance, we have the original mean, should be relatively easy to kind of determine what that distribution of our sample means looks like. Okay. So I was asking you to kind of find what the distribution of my sample means would look like, but instead of size 36, I took samples of size 100. So what should happen to the mean of my sample means if I change the sample size? So let's say now I'm trying to redraw this distribution or kind of visualize it. The mean of my sample means is always just the original mean of the data I'm sampling from. Okay? So if I change the sample size, what happens to my new mean? Nothing. It's not influenced at all by it. It will always be, doesn't matter what sample size I take, the distribution of my sample means should always be centered around whatever the original mean of the data I sampled from was. Okay? So it should be always centered around this 3,287. So right away, we know we're at what, A or C. The variance, well, actually here, I'm asking for the standard deviation of my sample means. But kind of those are really one and the same. So as I take a higher sample size, what should be happening to the variance of my sample means? Yeah, right, the denominator is getting larger. So instead of 36, I've now got 100. So it should be lower. Well, before we found it was 100. So I know my new standard deviation should be less than that. So I look up here, the only values less than 100 here would be 60. We already ruled B out. We said that the mean of the sample means is always going to be that 3,037. And so if I go ahead and calculate it, I actually end up finding that standard deviation has went from 100 and gotten lower, and the value that we end up, it decreases down to is 60. So if you did 360,000 divided by 100, that gives you your variance. Take the square root, you end up with that value of 60. Okay? So here that kind of, I don't know, you could have actually figured out what the new standard deviation was. I guess you could have chosen, sorry, what the new standard deviation was without actually calculating it, because as long as you look at this formula, well, right, we know that if we take a higher sample size, it should decrease that variance and decrease that standard deviation. Oops. Any questions on anything kind of between those two examples? Okay with that? Okay. So we've already kind of said this, but I have some different like visual here. But you can kind of see here, this is like drawing out the distribution for different sample sizes, 1 to 5 to 50, right? Notice as we go to higher and higher sample size, we get this more peak distribution, which is really just telling us now that if I get a sample size up to 50, I'm almost guaranteeing that I see a sample mean somewhere around where the true population mean is. If I'm only taking samples of size 5, well, it's still fairly likely I see these values that are pretty far away from wherever that true mean is. Okay? So we like to try to get as high of a sample size as we can. Okay? And it kind of is intuitive, right? The more observations in our sample, the more informative it should be, right? If I only have 2 people in my sample, well, those 2 people could look nothing like with the average of the population. But if I've got 100 or 200, well, it's very unlikely that all 100 or 200 look unlike the average person, right? So we're just kind of decreasing those chances that we're getting like a skewed sample when we take these higher and higher sample sizes. So I ran another kind of simulation, I guess, where I was randomly sampling from a variable that didn't start out as normally distributed. Okay. So I started out with a variable that was uniformly distributed. So notice when I took samples of size 1 and calculated the sample mean, all these values in between 0 and 100 were equally as likely for me to see as the sample mean. However, when I started taking samples that were of size 3 or 10, well, now it's way less likely that across 10 people, I'm seeing these values of 100 or between 0 and 10 that are really far from that mean of 50. Okay? And if I take samples of size 50, notice I'm almost guaranteeing, right, the probability I see something between 40 and 60 here is almost the entire area under the curve. Also, when I'm going up to the sample size of size 50, notice this distribution. I try to draw the line of best fit through it, really close to a normal distribution. So what ends up being true is if I can get, I knew that if I just sampled from an originally normally distributed variable, my sample means were also normally distributed. What ends up being true is no matter what the original variable starts out distributed as long as I take a sample size over 30, right, or 30 or higher, usually try to treat it, it's kind of said to be over 30, but we'll kind of see it even at 30, it's a really close approximation. But if I take a sample size over 30, my sample means, no matter what the original variable I sampled from was distributed like, my sample means will be normally distributed. Okay. So I will try to prove this to you with data. You can look up the mathematical proof. I have no guarantee that even a small percentage you have the math kind of prerequisites to where we could really walk through that proof and understand it line by line. To be completely honest, when I go back at it, it takes me some concentration to be able to kind of walk through the real analysis of line by line. But if we know this rule should hold, we can check it using some data. So as we take higher and higher samples, not only are we guaranteed that it's a really close approximation to a normal, the higher and higher the sample size gets, the closer and closer the approximation gets to that normal. So once again, another scenario, it's great to have large samples. Okay. I had this kind of visual, I steal some of these from the book if I like them. This one I really do like because it shows you 4 different variables. They all start out distributed very differently, right? We've got a uniform, kind of an exponential. I don't even know what we would call this one. And then we kind of have this parabolic kind of distribution. So no matter which variable we start out sampling from, if we take samples of size 2 and then calculate the sample means and then look at the distribution of those sample means, they start to look a little bit different. Nothing really looks normal here. If I take samples of size 6, notice that for some of those distributions, even at sample size 6, I've basically got, not really an approximation. I have a normal distribution there, right? Now, for some of those variables, I still have a normal distribution. It's definitely skewed a little bit in either direction. But remember, I said that we need at least to get to 30, right? Or have a sample size over 30 to guarantee that no matter what the variable we were sampling from started out distributed as, our sample means at 30 or above, notice all of these look just like a normal distribution. There's no skew to them. They have that symmetric kind of shape to them, right? So as long as we can get sample sizes over 30, we don't have to worry about what the original variable was distributed as. Yeah.
So this would be applicable to real life. So if you sample 30 people about anything, you get this distribution.
Yeah, I'll prove it to you with 4 different variables here in just a second. Yep. Any other questions here? All right, so we'll dive into this data experiment to prove this to you, right? So I had all these births in Indiana in 2004. I had the population data for Indiana births in 2004. So I can use that data to calculate the mean and the variance, or the standard deviation, for each one of these variables, right? And they will be population means and population variances. So I had birth weights, I had the length of the pregnancy or gestation, I had this health measure of the baby, the APGAR score, and then whether or not the mother smoked while pregnant. Okay. So you notice here, I don't even have to technically start out, and we'll talk a little bit more about it when I get through later on. We don't even have to start out with truly a continuous random variable. Right? As long as we're sampling from a variable, our sample means should be continuous. Right? Think about it this way with the maternal smoking variable. It's a 0 or a 1. They either smoked while pregnant, 1 or they didn't, 0. But when I calculate a mean, I don't see ones and zeros. If I see 22 out of 100 people smoked while pregnant, my sample mean there would be 0.22. I've basically taken the average of those zeros and ones. So then I'm guaranteed my sample means could be really anything between 0 and 1, right? Any decimal, any decimal point possible. And so I don't even have to start out with a continuous variable that I'm sampling from. I know that my sample means will be a continuous random variable, right? Or it'll be truly continuous. So anyways, I start out with this population data, right? I can take a look at each one of these variables. I can calculate their mean, their variance, and look at what the distribution was. Okay? So here, I calculated the mean of each one of these, right? So the average birth weight's about 3,000. I calculated their standard deviations here. Not really anything that is overly interesting. I mean, think about 9 months being kind of typical. Pregnancy, well, 38 weeks, so pretty close to kind of that what we think of as 9 months. The one that's kind of disappointing, well, pretty healthy babies, right? 10 was the highest. 18% of mothers smoked at some point in the pregnancy, which was to me a lot higher than I would have thought. It says older data, but still, right? Alarming for 2004. But we can use these means and we can use these standard deviations. And if what I was telling you was true, when I take a bunch of different sample means, I should see that the mean of those sample means are just these original population means for each variable. And I should see that the standard deviation is just the original standard deviation divided by the square root of my sample size. Now, not all of these variables started out normally distributed, so what we should also see if we take samples over size 30 is all the sample means should be normally distributed, no matter what the distribution of these variables originally looked like. Well, birth weight actually started out pretty normally distributed, right? This is one of those biological kind of markers that we just tend to see this show up a lot in nature, that it's normally distributed before we even start looking at the sample means. If I look at the length of the pregnancy, now I don't have something that's normal, it's definitely less skewed. We see a lot more premature births, 5, 6, 7 months. We don't really see any babies born at 11 months, right? That health distribution, it's actually not continuous. It's only an integer, kind of a less skewed distribution there. And I didn't put up the distribution of tobacco use because it would just be 2 bars, right? One at 0 that went up to 0.18 and one at 1 that went up to 0.82. Okay? So we started out with one variable that was normally distributed, but 3 others that weren't. Okay? So then what I did is that was all from the population data. Right? We were lucky we could actually observe those population means. We could observe those population standard deviations. I then went through and took random samples in Excel. You can use like a random number generator, create identification numbers, and randomly select 100 births out of these 87,000, I think it was. So I randomly selected 100 births. From those 100 births, I then calculated the sample mean for each of those 4 variables. I stored those in another file. I then randomly sampled another 100 births, calculated the means for those 4 variables, stored those in the other file. I continued to do that 1,000 times. I now had 1,000 different sample means for birth weight, 1,000 sample means for length of the pregnancy, APGAR score, and maternal smoking. From those 1,000 different sample means, well, once I stored them in a different Excel file, it was very easy. I used the average function, stdev.s, to calculate my standard deviations and my means of those 1,000 different sample means. Okay? So what should be true is when I calculate the mean of those 1,000 different sample means, and I calculate the standard deviation of those 1,000 different sample means, they should be equal to the original population mean and the original standard deviation divided by, well, here I took samples of size 100, so divided by the square root of n would actually just be divided by the square root of 100 or divided by 10. So when I look back here, all of the means for my sample means should be exactly what these numbers are, and the standard deviation for my sample mean should be all of these values. Move the decimal point 1 place to the left, right? Dividing by 10 would kind of move that decimal point to the left. So, sure enough, if I look at these, right, I'm off a little bit, right? This one, it looks like it's off by 1 gram. but actually, if I wouldn't have rounded it, it's only off to like the first decimal point. And these look like they're a little off. It's really only because I had to round to the second decimal point. This was like 0.267 something. So I am a little bit off, right? But first of all, we said they're close approximations. And if you look at the actual mathematical proof, in order to get exactly the population mean, I would actually need an infinite number of sample means. So you can never truly prove to yourself with the data using this method because you can't generate an infinite number of sample means. Now, if you do something like instead of 1,000, do 10,000 or 100,000 sample means, you end up with things that are close to each other out to the like 10th or 11th decimal, right? I mean, you can basically prove it to yourself without an infinite number. I only chose 1,000 because to do 10,000 takes quite a bit more work, and it kind of is pretty sufficient to just do it with 1,000 different sample means. Any questions on this? And I'm not even going to make you do the random samples yourself. I'm just trying to provide you some justification that this does hold. Right? So not only that we have some statements made about the mean of the sample means and the standard deviation of our sample means, but I also said as long as we took a sample over size 30, all of these different 4 variables, their sample means should be normally distributed. Okay? So I took those 1,000 different sample means for each variable, and I just made a histogram. Okay? So notice for birth weight, this is like as perfect of a normal distribution as you're going to see using data. Right? But what is kind of interesting to kind of relate this to the original values we saw for the variable, if we go back to the original population data, we saw birth rate really ranging from anything to 5,000 all the way down to like just incredibly small birth weights, right? These are like severely premature births. Okay? Well, if I was just looking at one birth, it might be that I see, one of these extremely low weights from a premature birth. But if I'm randomly selecting 100 births, to get a sample mean that's that low, I mean, it's very unlikely if I'm truly selecting these births at random, that I end up with 100 extremely premature, children or births. Right? So when I look at the distribution of my sample means, the standard deviation of the variance on that should be much lower because it should just be the original variance divided by the square of our sample size. So when I look at the distribution of those sample means, sure enough, I'm only seeing values as high as like maybe 3,500 instead of 5,000. And instead of as low as like 200 or 300, I'm only seeing sample means just above 3,000. Okay? So my sample means will always have a much narrower distribution than the original data I sampled from. Like I said, it kind of makes sense. If I do the income thing, I can always choose one person and see an average income of 500,000. It's unlikely I can choose 100 people and see their average income be 500,000. Right? So that one started out normal though, so I haven't really proven to you anything there, right? The other 3 that didn't start out as normally distributed, let's see if their sample means are also normally distributed. So we look at that length of pregnancy or gestation. Sure enough, we end up with sample means that follow really close to, this one, to say it's an approximation, this is like another perfect kind of normal distribution. The APGAR score is still normally distributed. We could argue maybe it still has a little skew to it. And this is likely because it started out kind of in this discrete manner. But still, if we approximate it with a normal, we're only going to be off when we try to calculate probabilities at very far decimal points. So we would kind of say that this is still a close approximation to a normal. Maternal smoking, same kind of thing, follows a pretty nice normal distribution. There's a couple like weird things going on here with some of the cutoff values, but that's more so because I had to force the histogram into this range. If I was to kind of draw more bars here, it does end up looking a little bit closer to a normal distribution. So even a variable that started out as a 0, 1, when we calculate the sample mean for it, we end up seeing this continuous range of values, and that follows pretty close to a good approximation for a normal distribution. Questions on anything here? Yeah.
I guess for the smoking sample, since it's only, how do you interpret this data? There's only a yes or no question we were asking.
Mm-hmm.
So like, how do you interpret this data? Like, what is 0.160?
Yeah. So what this is telling me is if I tried to think about the average here, the mean looks like it's somewhere around 0.17, 0.18, 0.19. So what it's saying is that on average, right, we're getting, whenever we deal with a 0, 1 variable, and I think we might get there today, if not for sure on Wednesday. If we're taking the mean of a 0, 1 variable, you think about really what we're doing is I'm adding up a bunch of ones and zeros to get my numerator, and I'm dividing by the number of total numbers I have. So when I have a 0, 1 variable, it's like 0 plus 1 plus 1 plus 0 plus 0, whatever those values end up being. Well, my numerator is really just going to represent the number of ones. So here would be the number of mothers who smoked while pregnant, and then I'd be dividing by the total number of observations. So it would be something like, in my sample of size 100, I saw 34 mothers smoked out of the 100 mothers in the sample. So we end up calling it as a proportion, right? It's still a mean, it's just a mean of a 0, 1 variable, which we know is going to be somewhere between 0 and 1, right? So really that sample mean for a 0, 1 variable is representing the proportion of mothers who smoke while pregnant. So all these values represent the proportion of mothers that smoke while pregnant. It's still a sample mean. We just think about it in a slightly different way because it has somewhat of a different interpretation.
Right,
Yeah. Does that answer?
Yeah, like if you replicated that in another state, that was like Indiana, you get close to the same values.
So if I replicated what I just did here,
Yeah, like if you did this state study in Kentucky, you'd probably get close to the same values. If they were
maybe, yeah. The only pushback I would say on that is it's possible that if we go back to the population data, these were only Indiana births. Right? So it's possible that the population mean in Indiana, that the proportion of mothers who smoke is 0.18 or 18%. It's possible that in Kentucky, their population mean might be higher or lower. I'm not going to pick on Kentucky, but I can probably guess which way it would go. Right? But yeah, if we're comparing across states, we have to be really careful about what we're defining as the population. Yeah. I probably shouldn't say that, but any other questions kind of related to this idea? So why are we building up all this up? It actually allows us to start thinking about how we can take this distribution of our sample means, and eventually where we're going to stop. I might introduce the idea today. I don't know if we'll quite get that far. Well, eventually this is going to lead us into something called confidence intervals. So that's what we're building up, but we needed to know that the distribution of our sample means was going to be normal, because it then allows us to think about things like this. So if I have my sample mean distribution, as long as I have a sample size over 30, I know it's normally distributed. I know the mean of my sample means is just whatever the original population mean, whatever I was sampling from was. And the variance of my sample means is the original variance over my sample size. Well, if I have a normally distributed variable, let's say I was using something like the birth weight one, maybe I'm interested in, well, if I take a sample of 100, what's the probability that I see a sample mean of 3,000 or lower? Well, I can actually find that probability if I can turn that value I'm interested in into a z-score. Because then it's just like what we've been doing before. I can look that z-score up in the table. The table tells me the area to the left. Now I've got my probability of seeing a sample mean of 3,000 or lower. So knowing that those sample means will be normally distributed, I can now treat this just like every other example we were doing, where we convert a normal distribution into a standard normal distribution and then start to find the probability of seeing values above a certain cutoff, below, in between, right? So it's going to look a little bit different, but the general idea of what we're doing is exactly the same. So I'm going to use the other side of the board. So I don't want to erase that, but I want to then show you before we look at the full kind of steps here, what's going to look a little bit different than what we were doing before. So we have already turned normal distributions into standard normal distributions, looking at this equation for my z-score, right? We just subtracted the mean divided by the standard deviation. Well, now we're wanting to turn values for a sample mean into a z-score. We're actually going to do the exact same thing, right? But now instead of looking at some value for variable x, we're going to be looking at a cutoff value for the sample mean, right? So you can kind of think about it as the thing or the statistic we're interested in. It's no longer just a value for a variable, it's the value for a sample mean. So then when we subtract the mean, we actually need to subtract the mean of the statistic we're interested in. We're interested in the sample mean here, so we have to subtract the mean of my sample means. We then also have to divide by the standard deviation of my sample means. So it's still the same format. The only problem is here, we know that the mean of my sample means is just whatever the original population mean was from the data we sampled from. So I can plug that in. What's the standard deviation of my sample means? So that was the square root of the original variance of the data we sampled from divided by my sample size. So the first step we'll do is make sure the central limit theorem applies. So we know we're dealing with a normal distribution for our sample means. Then we'll transform that distribution into a standard normal, which is going to be using it looks slightly different than what we were doing before, but really that's only because we plugged in equations that we knew would give us the standard deviation of our sample means and will give us the mean of our sample means. So I wrote a little bit different on the slides than I did here on the board, and that was just kind of me trying to start showing you both ways, because we'll see it depicted in both ways. Really, I'm just simplifying the mathematics a little bit here in the denominator from what I have in the denominator on the board. Any questions kind of over that? So I really want to kind of hammer home, like it's still the same exact format. It's just now, right? If we go back, really, we would have had to calculate the standard deviation by hand, right? And so there's always going to be an equation kind of floating around in the background when we need to calculate the standard deviation. But here, we've got a formula for the standard deviation of sample means, which we know will follow this, right? So we can just plug that in. Now, once I have my z-score, everything's the same as what we've been doing, right? Because I then take my z-score, I look it up in the table. Well, I think about what region I'm looking at. Then I look up that z-score, find that probability in the table. And then sometimes I have a fifth step, right? Here I didn't, because I just wanted to know the probability was below 3,000. But if I wanted the probability that it was above 3,000, what would I have had to do? Simply, subtract whatever I found from the table. So sometimes we have a fifth step, sometimes we don't, right? It just happens that we won that probability in the lower left. Okay? So once we get past this z-score, everything's exactly the same as what we've been doing. Right? Any questions on this one here? We'll put some actual values here and work through them now. So I'll leave this up over here. So we have that equation for the z-score. So I'm giving you here an original variable x that's normally distributed. We then take a sample of size 100 from it. And we want to know what's the probability we see a sample mean in between 10 and 15. So I took a sample of size 100. It's definitely over 30. So I know my sample means will be normally distributed. The mean of those sample means should be what? All right. Yeah, just the mean of the data I sampled from, which that was that random variable x, which had a mean of 5. The variance on my sample means should be that original variance of 2,500 divided by my sample size So the variance is 25, which means my standard deviation is just the square root of that, 5. So I'm then interested, okay, what's the probability I see my sample mean take on a value in between 10 and 15? So the next step is I need to convert those two values I'm interested in into z-scores. So here on my subscript, I'm just saying the z-score for the value of 10, z-score for the value of 15. So what I would then next do is, okay, I've got that value of 10. That's the sample mean value I'm interested in. So I would take 10, subtract the mean of my sample means, which I know is just the population mean of the original variable I sampled from. So that was 5. And then I would divide down here by the square root of the variance over my sample size. But if I've already done this calculation ahead of time, I should remember that this denominator is really just representing the standard deviation of my sample means, which I had calculated over here. I could just plug in 5 there. So this is actually kind of an easy one. If I would have went ahead and calculated that standard deviation before I even looked at the z-score formula, and I remember what a z-score tells me, how far away is 10 from that mean? The mean is 5. 10 is 5 away from 5. If my standard deviation on these sample means is 5, how many standard deviations away am I? Just 1, right? I'm 5 away from the mean, the standard deviation is 5. I'm 1 standard deviation away from the mean. Okay? Now I can plug that into my z-score equation, and sure enough, I'll find that z-score of 1. But if I calculate standard deviation ahead of time, sometimes the numbers work out kind of nice, that I can actually think about the definition of the z-score and really avoid making an error in my calculator. If the numbers are kind of nice, and then play out kind of nicely. And if I go ahead and do the same thing for 15, I end up with a z-score of 2. So I calculate those two z-scores. What's the next step? Use those z-scores, and I look them up in the table. So if I go to 1.00 in that standard normal table, it'll give me the area to the left of that z-score of 1. If I then look up the z-score of 2.00 in that standard normal table, it'll tell me the area to the left of that z-score of 2. If I want the probability of being in between those, what would I do? Subtract that blue area or the smaller area from the larger red area. Okay? And that would just leave me with, right, everything here would cancel, and I'm left with just the probability of being in between. Any questions on this? So I go ahead and look those up. I think I find 0.84 and then 0.977. And that's just a matter of taking the difference between those two, right? So that I kind of, this brick area kind of subtracts from the light blue area, and all I'm left with is what's in between. Questions on this? Okay with this? All right. So I'm gonna have you guys work through one. So let's say that I've got right some variable like the pregnancy here, gestation, and I know the population mean is 39. Somehow I'm able to observe this. I also know the population variance is 9. If I take a sample of 81 births, what's the probability that I see the mean gestation with a sample mean value of 39.5 or greater? So I would draw this out, right? You're looking at the distribution of sample means. You've got the original population mean of the data you sampled from. So before we had kind of 5, now that would be what? 39. You can use the variance on the original data you sampled from to find the variance of your sample means. You can use this z-score equation to turn that value of 39.5 into a z-score. Look that value up in your standard normal tables, and then find the probability of being above 39.5. Remember, the table always tells you the area to the left, so when we look that z-score up, we'll find the area to the left. And you want the area to the right, so you might have like one more step there at the end. So work with the people around you. I'll give you a couple minutes to work on this. And then I can kind of see where we're going, have some problems, and then we'll talk about it kind of coming together here after you work on it for a bit. Kind of even with your visual, think about what values you can actually narrow it down to as well. Oops, sorry. All right, so see a lot of people working, so I'll be nice. I'll leave this open and kind of talk through. So I'm thinking about the distribution of my sample means here. What should they be centered around? What should the mean of those sample means be? Yeah, just whatever the mean of the data I sampled from was. So I was then interested in what's the probability that I see. I'm going to run out of room here. Well, I'm going to move this over. So we know that the mean over here was 39. I want to know the probability of seeing 39.5 greater. So what I need to do is turn this into the z-score. Now I've got my equation for the z-score over there, kind of all in one. But I think, and hopefully you'll kind of see that this allows us to sort of think about things in a slightly different way maybe visualize it easier without having to like always use a calculator, especially if it's a multiple choice problem. If I first calculate the standard deviation, kind of do the intermediate calculation, right? I know this denominator represents the standard deviation of my sample means. So I'm just going to go ahead and calculate that instead of like combining two formulas. So if I take the square root of what? My original variance of 9 over the sample size of 81, I believe I'll get 1/3. Okay. So here is where when we start dealing with sample means, it starts to get a little confusing. And I tried to bring this up in some examples we've done in the past, but there's just not as many where it's obvious as once we get to sample means. Remember, when I'm drawing this, I'm just kind of drawing it to the left or the right. I don't know if I'm drawing it to perfect scale. Because even though 39.5 seems like it's really close to the mean, right? It's only 0.5 away. When I'm thinking about the probability of seeing that or anything greater, or how many standard deviations away from the mean 39.5 is, well, if I'm 0.5 away, but the standard deviation is 0.1, I'm still 5 standard deviations away, right? So here, when I have a standard deviation of 0.33, but I'm 0.5 away, well, that means I'm almost like, I'm more than 1 standard deviation away. It's like I'm 1.5 standard deviations away, right? Sure enough, if I plug all my values into that z-score equation, I end up finding that, yeah, being 0.5 away from the mean is actually being 1.5 standard deviations away. Right? And we're probably not the most comfortable yet with, well, how, is 2 standard deviations far away or is 3? We kind of said in the past, being 2 standard deviations away or more, pretty unlikely, right? That probability is pretty close to 0. So if I'm thinking about the probability of seeing 1.5, something that's 1.5 standard deviations away from the mean or even greater, it probably has a relatively low probability, right? I automatically know that the probability has to be less than what value? So what would the probability of seeing 39 or above be? 0.5. So seeing 39.5 or above is just going to be smaller than that, right? This area is 0.5. I want an area that's smaller than that. So if the mean always splits that distribution in half, the probability of seeing something above the mean is 0.5, which then if I want to find the probability of seeing something above the mean or greater, it has to be less than 0.5, that probability. So I can right away rule out what? C and B. So I know I'm either going to be at A or D. Well, being 1.5 standard deviations, it's more than 1 standard deviation away, which is starting to get kind of further away. So if I was guessing, it's probably going to be a little closer to 0 than it would be to that total area of 0.5. Okay? So if I'm guessing here, I probably think it's A. But I can actually look up that z-score of 1.5. What area do I find in the table? What value do I find in the table? Anyone get to this point? Yeah, if I look up 1.5, 0.9, say 993, yeah, there we go. Well, I wanted the area to the right, so I still have to subtract it from 1. So 0.06 without 668. Okay. Any questions on kind of any point along this problem?
Can you show us how you found the, you just plug in the numbers for the z-score?
Oh, yeah. So all I did there was,
I guess I got probably confused on something.
yeah, it's kind of tricky. You're doing this in steps, but if I take this, it's 39.5 was that value I was interested in. Yeah. Subtract the mean of 39. Divide by the square root of, what was it, 9 over 81. Yeah. So this is where sometimes doing things ahead of time makes it a little bit easier, because if I had found that this was just 1/3, I could have taken 0.5 and divided it by 1/3, right? So I can see the difference is 0.5. I know the standard deviation here I found was 1/3. Maybe it makes it a little bit easier than that. Okay. Any other questions on that? It's still open. 21 people have answered. All of you should answer, and hopefully everybody should get this one correct. This work through it together. 21 of us here. Make sure you answer. If you answered already, you can change it. Whatever the last answer you respond with, it counts as correct. Okay. All right. I'm going to close it out. I got 22 of us. All right. So this kind of has everything we worked through up on the board. You just want to go back and have this as kind of a reference, right? But we worked through everything together up here on the board. The next thing that I'll introduce today, I don't know if we'll quite get to a problem. We might get through one, but it's really similar to what we have been doing with the sample mean. So the sample proportion, right, was, we already talked about it or alluded to it earlier when I said really all a sample proportion is the mean of a 0, 1 variable. Okay? So it kind of goes back to when we were talking about the binomial. Binomial, we either saw a success or failure, 0 or 1. Right? So when we thought about the mean number of successes, right? The mean number of successes was just n times p. Well, here, if I want the mean for the proportion of successes, that would just mean take the number of successes, n times p, and divide it by the total number of observations. So this just ends up being t. Right? So we're thinking about, for our sample proportions, the mean of our sample proportions will just be whatever the original population proportion was. So if I'm flipping a coin, and I flip it 100 times, the proportion of times it comes up heads, right? Well, if I flip it any 100, maybe sometimes I see 60 come up heads, and other times I see 48, one time I see 53. But if I did this enough times, I flipped the coin 100 times, enough times they had like 1,000 different samples, those sample proportions should be centered around whatever that true population proportion was. We go back to that maternal smoking variable. I won't go all the way back to the slides. But remember, when we look at the sample means, it was centered right around that 0.18, which was like the population proportion. What ends up also being true is that if I'm thinking about the standard, actually, I'm thinking about the variance for my sample proportions. Well, if the variance on the number of successes is n times p times 1 minus p, the variance on the proportion of successes will just be that divided by n. This cancels, and the variance of my sample proportions is just p times 1 minus p. Okay? So when we're thinking about, and I said, here, when I was talking about this one, I should have been talking about, sorry, the variance of just my proportions, not my sample proportions yet. Okay? So here was the variance just on the original proportion. So if I want the variance on my sample proportions, well, remember with the mean, we were just taking the original variance, dividing it by the sample size. So here, the original variance on proportions was p times 1 minus p. I then divide that by n, right? And so the variance of my sample proportions is that p times 1 minus p divided by n, or the standard deviation, just take the square root. And those sample proportions should be centered around whatever that true population proportion is. I mean, it's a little bit different what we're doing with means, but it's really only because we can calculate the variance a little bit differently than actually having to go through and doing it by hand, find the deviation from the mean squared, divided by the number of numbers we had. For a proportion, you know, it will always follow this equation, kind of stemming from what we talked about with the binomial. Questions on that? So, if what we did for the sample mean looked like this, and we said we could plug in the equation we had for the standard deviation sample means, but the general format of it is going to be the exact same for the sample proportion. It's just now we're interested in some cutoff value for the statistic we're interested in, which is the sample proportion, not the sample mean. We'll subtract the mean of that statistic we're interested in, and we'll divide by the standard deviation of that statistic we're interested in. the exact same format as before. It's just now we've got slightly different equations or slightly different notations for what these things represent. So now we'll take that sample proportion we're interested in. The mean of my sample proportions is just whatever that true population proportion is. And then the standard deviation of my sample proportions would be, right, square root of the variance here. So if we're going to do this all at one time, and all within one formula instead of calculating immediate values, we're going to have a slightly different equation for our z-score. But it's still following the same principles. We're still subtracting the mean of the statistic we're interested in and dividing by the standard deviation of the statistic we're interested in. It's just that standard deviation is a slightly different equation than what we questions? So, what if we had this example where I want to know what's the probability I see 55 or more coin flips come up heads if I flip a coin 100 times? So it's a little bit tough in that we're no longer directly sometimes given a sample proportion, kind of like we were told what the sample mean we found was. Right? Here, I'm thinking about the distribution of my sample proportions. I flipped the coin 100 times, so my n is 100. So I definitely met that central limit theorem. So these sample proportions should be normally distributed. I use the coin flip example because that way I know that the mean of my sample proportions is just equal to that true population proportion, which if it's a fair coin, is just 0.5. Okay. And then I'm interested in, okay, what's the probability I see 55 or more heads? Now, if I'm dealing with a sample proportion, a proportion has to be somewhere between 0 and 1. So I've got 55. How do I turn that into a proportion? If I'm flipping the coin 100 times, my sample proportion would just be the value I'm interested in is 55 out of 100, or 55 over 100. So here, right, I'm interested in the probability of seeing 0.55 as my sample proportion, or anything greater than that. Is that clear how I came up with my sample proportion there? So a lot of times it's phrased as, well, what's the probability I see this number of successes out of this many attempts? Well, to convert that to a proportion, just take the number of successes divided by the number of attempts. From here, we're going to turn that value we're interested in, 0.55, into a z-score. How do we do that? If we go back over here, we have this equation that gives us the z-score for sample proportion. So what am I going to plug in here? What's my sample proportion? Yeah, 0.55. The true population proportion of flipping a coin was 0.5. And then divide by the square root of 0.5 times 1 minus 0.5 divided by my sample size of 1. Okay. Once I have the z-score, it's just like what we were doing before. So I think if I plug this in, I end up with a z-score of 1. Okay. So I can go to my table. We've kind of already looked this up today. So my z-score is 1. Go to that table, scroll down, looking for 1.00, so 0.8413. All right. But I'm not quite done. Oops, not over there, over here. Because 0.8413 is the area to the left of that z-score. I wanted the area to the right. So 1 minus that. All right. So what? 0.1587, I think. Any questions or anything kind of on that one? So I'm gonna have you guys kind of end on this one. It's gonna be a very similar idea. All right. Still got a fair point. So that true population proportion should be 0.5. The sample proportion you're interested now in finding the probability of seeing that or anything greater would be 66 out of 144. So I'll help you out a little bit here. Instead of 55 out of 100 now, my sample proportion I'm interested in will be whatever that 66 out of 144 is. Your new sample size is 144. Kind of draw this out and try to come up with what your new z-score is. Look that z-score up in the table. You still want the probability of seeing that or anything greater, right? So once you find that probability in the table, you'll then have to subtract that from 1. Okay. So I'll give you about 3.5 minutes here, and we'll kind of go quickly through the answer, and we'll kind of end class on that. I have one more thing to mention before we get out. I'll duck down in case anyone wants to see this. All right. So if you haven't gotten an answer in, take your best guess here. You should be able to narrow it down to 2. We'll kind of talk about quickly why. All right. So respond with what you think the correct answer is here. I'm going to close it out. So hopefully we get what 22 of us we had before. 1 person left. So I'm going to close out. Make sure you get an answer in. So we got 21. I think 1 left. So all right. So what 2 could you rule out right away? I know that true sample, that true proportion is 0.5. 66 out of 144 is a sample proportion that is 0.4 something, so less than that. So automatically, you know that probably has to be greater than 0.5. From there, it's just using whatever that sample portion is, 0.4 something. Plug that in as your sample portion value, 0.5 here, and my new sample size is 144. If I do that, I believe I get a z-score of -1. I can look that up in the table, but if the area to the right of +1 was 0.1587, the area to the left of -1 would be 0.1587. I then want the area to the right, I'm then subtracting that from 1, right? I don't know why I have 0.8 here before. Sorry, this should be 0.1587. Subtracting that from 1, we should get that 0.84. Okay? So we will pick up with the proportions next class, but one thing I am going to do is I'm going to get a Learn Smart up for the next topic we're going to talk about, which is confidence intervals. I'm going to expect that you went through that before we start class on Wednesday. We got, just about 2 days to go through and do that. It should take 10 minutes. It's the one that's just graded for completion. I think I call them Learn Smart sometimes. I think they're actually called Smart Books. They change the name and I always forget. But it's the same idea, right? So I'll get that posted when I get back to my office. I'll expect that you've done that. It's due before we start class on Wednesday. Okay? All right. We'll see you guys on Wednesday.